Welcome to the Explainer. Today, we're diving into a really cool question: how do you actually teach a computer to see? We're going to break down how an AI goes from just looking at a picture to really finding and understanding the stuff inside it.
All right, let's just jump right in with something that's, well, dead simple for us. Take a look at this image. Is there a car in it? I mean, your brain probably answered that before I even finished the sentence, right? No effort at all.
Yeah, of course it's yes. But here's the thing. For an AI, that easy yes is just the beginning of the story. Because, in the real world, just knowing a car exists in the picture, that's often not nearly enough.
I mean, think about it from the perspective of a self-driving car. It can't just know, yep, there's a car somewhere around here. It has to know exactly where that car is. And not just one car, but all of them. How many are there? Where are they? A simple yes is totally useless for not crashing. It needs the details.
So, this whole needing more detail thing brings us to the different ways a computer can see. It's not just one skill. It's more like a ladder of understanding, From super basic to incredibly specific.
Okay, so at the very bottom rung of that ladder, you've got something called classification. This just answers the "what is it?" question for the whole picture. The AI takes one look at this, and its only job is to say dog. That's it. It doesn't know where the dog is, just that a dog is somewhere in the frame. All right, moving one step up the ladder, we get to localization. This is where it gets a bit smarter. It builds on the first step by answering the "where is it?" question. So now, the AI doesn't just say dog, it also draws a box around the dog. See? It's starting to actually pinpoint where the thing is.
And then at the very top, for the most detail possible, you have segmentation. This is way beyond a simple box. The whole point here is to identify every single pixel that belongs to the dog, basically creating a perfect outline. Think of it like this. Localization is drawing a square around a statue, but segmentation is tracing its exact shape, every little curve. Okay, so here's the key takeaway for what we're talking about today. The thing we call object detection is really that powerful combination of the first two steps. It's the AI's job to figure out both what something is, that's the classification part, and where it is, that's the localization part, with the box.
Right, so that sets up a really interesting puzzle, doesn't it? How on earth do you train one AI to do two different things at once? Like, how does it learn to be good at both naming an object and drawing a box around it at the same time?
So let's think about that. Is what we're doing here a classification problem, picking a label like cat or dog from a list? Or is it a regression problem, predicting a bunch of numbers like the exact coordinates for the corners of a box? Well, what's so cool about this is that the answer is, it's both. It's not one or the other. A good object detection model has to master both of these skills. And the secret to how it learns is that it basically gets a report card that grades it on both things simultaneously.
So when it's training, the AI gets what we call a loss score. You can just think of it as its final grade. And that grade is made up of two parts. You've got the score from the what game, how good was it at guessing the right label, like cat or dog, and then you've got the score from the where game, how close was the box it drew to the actual correct box. You add those two scores together, and that's his total loss. This forces the model to get really good at both games to get a high grade.
Okay, that's great for one object in a clean picture. But how does this work in the real world? Because, let's be honest, the real world is messy. It's not one dog in a field, it's a dozen things all happening at once. And this is where things get really, really hard. Think about it. The computer has no idea if it should be looking for one object or 100. The objects can be huge, or they can be tiny specks. They can be camouflaged against a busy background, or even halfway hidden behind something else. The AI has to somehow figure all of that out. So the first idea people had was basically a brute force attack. It's called a sliding window, and the logic is super simple. Just check everywhere. Literally. You take a little rectangle, you check what's inside it. Then you slide it over a tiny bit and check again. And you just keep doing that. Slide and check, over and over for the entire image with every possible size of box you can imagine.
It sounds thorough, right? But let's really think about what checking everywhere means. For just a typical, not even that big image, say 500 by 300 pixels, how many boxes do you think we'd have to check?
The answer is 22.5 billion with a B.
Trying to run a powerful AI model 22.5 billion times just for one picture? No way! It's just computationally impossible. It would take forever. So that brute force idea was a complete non-starter.
So, okay, clearly we needed a smarter plan, a more elegant solution. Instead of looking everywhere, researchers had to figure out a way to look smarter. They needed to shrink that search area from billions of boxes down to something, well, something actually doable.
And that's where the big aha moment came in. It's an idea called region proposals. And the genius of it was flipping the whole problem around. Instead of grabbing a box and asking, is there an object in here? The new question became, hey, where in this picture are the spots that just look interesting? The places that are even likely to have an object in the first place.
So here's the clever part. A really fast, pretty simple algorithm just zips across the image. It's not looking for a car or a person. It's just looking for blobs, areas that stand out because of their color or their texture or because they look like a contained shape. It has no clue what they are, just that they're interesting. This gives you, say, about 2,000 potential boxes. And now, instead of running our big, slow, powerful detector billions of times, we only have to run it on those 2,000 promising spots. And this just shows you what a massive difference that makes. You go from the brute force method of checking billions and billions of boxes to this super smart selective strategy that only checks a couple thousand. That is the shortcut. That's the trick that made all the modern fast object detection we see today even possible.
And this is what it all leads to. We started with a super simple question, is there a car? And we end up here, with a machine that can look at a crazy, busy street and, in real time, find and track every person, every car, every traffic light. It's just a phenomenal leap. So it kind of leaves us with this big final question, right? We've gotten really good at teaching machines how to find stuff. But what's the next step? How do we get them to actually understand what they're seeing, to get the context, to see how objects relate to each other, to figure out what's about to happen? Now that's the next great challenge for AI.